I could also do with somebody testing out for me. There was somebody apparently has phoned from Driffield this morning to say they've been trying to watch the live stream and there's no sound. There's actually a parent of somebody who said that they've given up. I think there is no sound. Could somebody with a phone that was able to do this kind of thing? James, welcome to that's brilliant. If you would like to... But it's going to sound really odd in here because you're in the same room as it. Is that echoey sound that you were getting there, is that what it's like? Could you just kind of pop out of the room and test it? Because that's awful, that sound. It's very echoey, isn't it? I wonder what we can do about that. Is that any better? Is anybody... Have I improved it? Nobody knows. No? I've fixed it. Is that better? Wow. Right. Okay. I'm hoping that the sound is working and a little bit better. Has anybody got it on? It doesn't really work if everybody has it on at once because then you can't tell. Is that sounding a little bit better? Okay, it's delayed, but that's fine. Right. There is a register coming around. Look at this, an official register this time, not just a scrappy bit of paper. Core 1 to Core 2, step up in class, clearly. So we've now got a register with lines on it. If you could write your name on that, that would be ace. Right, we're going to do similar to what we did this morning. It's going to be the same format. So you should have 2 bits of paper in front of you. One of them says Core 2 revision list. They're over here, aren't they? Right. So, in the same way as we did this this morning, they are the topics on Core 2, and we're going to do it in approximately that order. So we're going to go through algebra, exponentials and logarithms, sequences and series, binomial, trigonometry and integration. And again, we'll use the exam paper and we'll pull apart the exam paper and do the same deal as we did earlier, where we look at particular questions that help us with that. We have a similar problem actually, I think, with this one, in that the exam board in this paper that we're looking at has merged a few of the topics together, so we can't do them strictly in the order that we would like to, but we'll be okay. I'm going to start with algebra. So, thinking through what we have for this one. Use the other pen. So I put down my black pen. There it is. Right, algebra. Just kind of one interesting thing looking ahead. You know, next year, as some of you will be aware, others may not know, next year A-level maths is changing quite considerably. So you're the last year of the modular course, and it's been the same modular course. Basically, the content of maths has been the same since the end of the 1990s. That was the last significant change. So, it's been like this for a long time. And this bit, we're talking about factor and remainder theorem. The factor theorem continues to be on A-level maths next year. The remainder theorem isn't. It's not a big a deal, really. So factor theorem. And the factor theorem, you don't really need to be able to quote this, but if you are forced to, says if f of a equals 0, then x minus a is a factor of f of x. And all it's basically saying is if you can find a value that makes your answer 0, then you've found a factor of the expression. The remainder theorem, and actually there is an argument that would say that I've just written these the wrong way around, because the remainder theorem really kind of in some ways should come first. The remainder theorem says that when f of x is divided by x minus a, then the remainder is whatever you get when you sub a into the function. Can you see how they could have come the other way around? Because if we start with the remainder theorem, then the factor theorem follows as a logical progression from the remainder theorem. The factor theorem kind of says, if you happen to stumble upon 0, then big news, you found a factor. So you can think of it the other way around. You'll sometimes see these written where instead of f of a and x minus a, it talks about ax plus b and f of minus b over a. You get the idea. It's whatever makes the bracket 0 is the number that we're working with. That's the x value that we're interested in. So that is the factor and remainder theorem. Some of you have. It's gone again. I don't know if there's anywhere I can stop it from doing that all the time. Some of you have seen my kind of current obsession with this calculator, the Casio FX9N1EX. You may have seen an unboxing video on YouTube.
Is that the same one you used in your unboxing?
No, this isn't the one that I used in my unboxing video because I can't find that one. I don't know where it is. I feel very sad about that. This is a new one, and look, I've written S6F Maths on the back of it in scruffy green marker so it doesn't get lost. But this is, you can, certain advantages with this is that you can solve equations with this straight away. It's by no means essential, but it is £22.47, or is it 74? What are we charging for it? Don't you know? It's about £23 worth of fantastic calculator. We'll see if we can use that in the question. Are we ready to do the exam question? I think we're looking at, it's an odd place to start, but we're looking at question 7 in the paper. I've put down my questions somewhere, I don't know. So, question 7. says, is that the 7 that you've got in front of you?
Yeah.
Good, I have given out the right paper, that is good news. So, it's the one that went out on the replacement paper, not the original paper that was on the pile, which was wrong. There are some here. It's the May 2009 paper, it's the one that you should be on. Can you share for now? In fact, I've given away my copy as well. Are there any more spares of the exam paper anywhere? Yep. So kind. Josh, have you got one? Right. The polynomial f of x is given by 2x cubed plus 9x squared plus 11x minus 8. Find the remainder when it's divided by x plus 2. We've just written down the remainder theorem, you've learnt it, it's on your poster, you've memorised it, you chant it in the street. If we're divided by x plus 2, that means we're interested in f of minus 2. So we're going to substitute minus 2 into this expression. F of minus, I don't know, I've written that twice. F of minus 2 is 2 minus 2 cubed plus 9 times minus 2 squared plus 11 times minus 2 minus 8. You know that terribly well. And all it is for us to evaluate that. You could do it on a calculator if we really want to, but that would be minus 16 plus 36 minus 22 minus 8. Is that minus 10? Are we happy with minus 10? Look at that, 2 marks straight away. Nice start. I don't know how widely I've said this and how widely Paul and John have said this as well. You know, there's no requirement for you to do the questions in an exam paper in any particular order. You certainly don't have to start with one and work through all the order that they appear. You can do them however you want. And that looks like a really easy 2 marks. I might have been inclined to think I could do that. You know, glance through the paper, get 2 marks under my belt straight away and maybe do the rest of it, but maybe move on. Use the factor theorem to show that 2x minus 1 is a factor of f of x. So that is f of a half. If it's 2x minus 1, the value of x that makes that 0 is a half. So we're going to sub a half in. What am I doing? 2 times a half cubed plus 9 times a half squared plus 11 times a half minus 8. One of the things this morning that I kept saying, do your answers as if you're writing for somebody that doesn't get this stuff. So make it really clear. I've shown exactly what I'm doing here. It's a calculator paper, so you could probably go straight for the answer from this. What's that? 2 times an eighth is a quarter, plus 9 over 4, plus 11 over 2 minus 8. That should be equal to 0, shouldn't it? That is 9, that's 10 quarters, so that's 5 halves, plus 11 halves is 16 over 2. Take away it, that is of course 0, isn't it? So that's it. Therefore, 2x minus 1 is a factor. Great. Okay. Express f of x as the product of a linear factor and a quadratic factor. I have got this here. I don't know that this would be particularly useful in this question, but just while it's here I thought I'd show you. if you can you see that? Is that coming across on the screen? If you go in the calculator to the bit that says, if you scroll down to where it says equation, there's a bit where you can put in a polynomial. So option 2 says polynomial, and then we're doing a polynomial of degree 3, and the coefficients here were, it was 2x cubed, sorry, plus 9x squared plus 11x minus 8. And if we put that in and press equals, it says that one root is 0.5. That was our 2x minus 1. The next root is minus 5 over 2 plus 1.32287 and so on I. And the next root is minus 5 over 2 minus that times I. Don't worry about the fact that I appears in there. It just means that those second two roots are not real numbers. This equation has only one real root. That's kind of answered part 4, although that's not a sufficient answer. But anyway, that's just to give you a little indication of what it can do. If the question had just asked us to find a root, then we could have done that straight away, couldn't we? We could have found half as a root on the calculator that way. Part 3. Express f of x as the product of a linear factor and a quadratic factor. Again, this is long division, isn't it? This is really saying divide 2x cubed plus 9x squared plus 11x minus 8, divide it by linear factor. And I don't want to dwell too long on this. You can do this however you have practiced this and however you feel confident. Some of you may be doing the bus stop method of writing the bus stop and putting things in and doing long division. Some of you may be using what John, I think, calls forced factorisation, the idea of just writing out the two brackets and working out what must go in the gaps. Some people have been using a grid method for this, which I think I will do now, because I quite like that. The grid says we're dividing by 2x minus 1. This term here, the first thing is 2x cubed. I'm going to think, what do I multiply 2x by to get 2x cubed? The answer is x squared, so I'm going to write that there. X squared times minus 1 is minus x squared. But I was supposed to have 9x squareds. I've only got minus 1 of them. To get from minus 1 to 9, I need to add 10x squared. If that's 10x squared there, what did I multiply 2x by to get 10x squared? The answer is 5x. 5x times minus 1 is minus 5x. At the moment I've got minus 5x's, I'm supposed to have plus 11 of them. So to get from minus 5 up to 11, I need to add 16. 2x, what do I multiply? Oh, 16x, sorry, what do I multiply? The answer is 8. 8 times minus 1 is minus 8. I've got minus 8. I'm supposed to have minus 8. I have no remainder. You don't need to write that in. Therefore, so the question says 6 minus 1 times x squared plus 5x plus 8. As I say, there are many ways that you could do that. Arriving at that answer is the important one. I quite like that grid method. I only learnt it last year. There was a couple of students in my lower sixth last year who came up with that as an idea, and I really liked it. That's got our 3 marks. Part 4. State the number of real roots. Well, the calculator has told us that there is one real root. How can we justify it? It says give a reason for your answer. Now, how can we justify that? Well, the question is, how many roots does that give us? And just because we wrote about it this morning as part of Core 1 doesn't mean the discriminant isn't something you can talk about as part of Core 2 as well. So if we look at that quadratic equation, were we to try and do something with that, b squared minus 4ac is 25 minus 4 times 1 times 8. That's 25 take away 32, that's minus 7. And the fact that minus 7 is less than 0, therefore we have no real roots from the quadratic. So only one root, which was x equals a half. Okay, so that's the bit. We need to justify that the quadratic part of it has no real roots. We do it using the discriminant. That's quite an important idea, isn't it? That sometimes we make the mistake of thinking that somehow core 1 and core 2 are separate, and the things we learnt about in core 1 you won't be asked about in core 2. But clearly, you know, the way to answer that was core 1. It was a core 1 bit of work, that really, wasn't it? That's 9 away, just like that. 12.5% of the paper done. My next topic is logarithms. Okay, logarithms. Shall we see how many people are watching on the screen? 8! We've got 8 viewers. Hooray! It's quite impressive. Right, logarithms. So, in core 1 this morning we wrote down a load of rules about indices. This is the other side of that. So it's the same rules, just revisited. The main thing we need to remember is that if we write that statement about indices, about powers, logarithm is just another word for power, it's just talking about the same thing, but that statement, another way of writing that is to write log base A of C equals B. They mean the same thing. It's pretty central that we understand that relationship there, because that's all that really matters about logarithms. We then have some laws to remember about how these behave, and they all come from the equivalent things that we did in core 1. So in core 1 we said if you multiply two things together, you add the powers. In core 2 we say if you add two logarithms, then you multiply the thing that you're taking log of. In core 1 we said that when you divide, you subtract the powers. So in core 2 we say that when we subtract the logs, it comes from dividing the thing that we're taking a logarithm of. In core 1 we talked about multiplying powers together when you raise something to a power. In core 2 you say if something is raised to a power, then that comes from multiplying. And you see how they're all linked together, these things. In core 1 we said that anything to the power of 0 gives us an answer of 1. So in core 2 we write the logarithm of 1 must always be equal to 0. In core 1 we didn't write, because it was a bit dull, that anything to the power of 1 is the same. The power of 1 doesn't change it, but we do think of that in core 2, because we say that the logarithm of anything to the same base gives you an answer of 1. And there we are. We did, I talked about it this morning as being, I wasn't sure whether I was talking about a core 1 thing or a core 2 thing, but that's the graph of a to the x, goes to 1 there. We definitely in core 2 we do need to know that graph. It's important that we remember that. It's probably worth knowing what the graph of log base A of x looks like. We'll talk about it a lot more. You know, when you come back after May half term, we're going to start on core 3, and as part of the core 3 work, we'll start with logarithms. We'll do some differentiation, but it'll include a little bit of logarithms. And we will learn about the graphs of these then, and about the relationship. It's not drawn terribly well, but that is y equals log base A of x. It's not drawn terribly well because that line there was supposed to be a line of symmetry with the line y equals x. But as I say, that's kind of, we're getting into a little bit of core 3 stuff in that. Right, I think there are 2 questions on this paper. They use logarithms, and we're only going to do one of them right now, if I'm right on that. We are going to do question 3 because that's just a really good example of this stuff. So it's question 3, and then we're not going to do just yet question 9, because I think question 9, yeah, I want to do the integration bit before we do question 9, so that'll come a little bit later. Right, question 3 says, use logarithms to solve the equation 7 to the x is 2 to the x plus 1. I think look out for this kind of question, because one of the things to remember about this, when we talk about logarithms, a kind of classic question to solve with this stuff is something like that: 5 to the x equals 24. And kind of a little bit of a history lesson going back a while, you used to have to do this with log base 10, because older calculators only have a log base 10 button. The calculator that you have, I think for just about everybody, has a button where you can change the base. So if you want to solve that equation, you could either take logs of both sides, bring the x down to the front, and then divide. So log 24 over log 5. You could do that way, and that's the way that you always used to have to do it, because you didn't have any other choice but a log base 10 button. Now you could do this same question by writing x equals log base 5 is 24. That's 5 to the x is 24, so it's the same thing. And you can do that in your calculator straight away by typing it in. So if we do log base 5 of 24, we get 1.974, 1.975, sorry. And if we do log, I noticed this the other day, the first calculator I've seen that doesn't have a log base 10 button on its own. Or am I just missing it? Is there anywhere it just says log? I wonder if I just write it without putting a base in, if it'll do it. Does it?
Shift and minus.
Oh, shift and... Oh yeah, so it is. There we go. So if we do... If we do that, then you get the same answer, 1.975. I was amazed when I saw that it's lost the log base 10 button as a standalone button. Astonishing. Anyway, maybe those who don't follow calculators so keenly don't care. Maybe your lives are richer in other ways. Right, if we're going to do this then, the point of that is that this question doesn't lend itself to that method of just writing x equals log base. I mean, what would it be? X equals log base 7 of 2 to the x plus 1. You could write that, but I'm not sure that that's got you any further. You see the issue with this? That actually they're designing a question where the sensible thing to do is not to rely on the button on your calculator that shortcuts it, but actually to go through the full thing of writing log in front of both sides with base 10, and then doing the proper bit of working out. So bringing the power down to the front, and then rearranging this in whatever way you want to. I think I am going to multiply out this bracket. So it looks like that. That's x times log 2 plus 1 times log 2. Collect like terms together. Factorise it and then divide. And this really is something that you're not going to do without a calculator. So we're going to put that in together. Sorry, I'm going off the edge of the screen a lot now. and I got 0.553. Do you agree with that? That's the answer to three significant figures. There we go. Is it better with the light? It is better with the light on, isn't it? Shall I leave the light on? Is it it's a bit too bright? I'll turn it off. That's good for us, isn't it? Right, there we go. That was question 3. Question 9 on this paper comes back to logarithms again, but we'll do it all together with the integration at the end of the afternoon. You're welcome to it. Remember what I said this morning about those kind of questions where one line of writing, a big chunk of marks, 5 marks for just one line of writing. No scaffolding, just straight into it, deal with it how it is. That's quite tough, isn't it? But we got that. Okay, I'm leaving logarithms behind and going on to sequences and series. I think we're pretty much in the order that we did things, aren't we, with this? Is that right? December, we started by doing some factor theorem, remainder theorem around the time we call one mock. Then just before Christmas we did some logs. Then we just started, I know with my groups it was a bit mixed up because it was a little bit before and a little bit after Christmas. We started APs and GPs and then finished it off after Christmas. So that's what we're looking at. And this is all about what's on the formula booklet. In Core 1, the best thing you can do with the formula booklet is take it off your desk and put it under your chair out the way, because there is nothing in there of any value at all. But in Core 2, you actually have some stuff that's useful. So it's on that first page, and it says for an arithmetic series, an arithmetic progression, the nth term is a plus n minus 1 times d. The sum of n terms, and it gives both formulas. It says n over 2, 2a plus n minus 1d, and it says n over 2, a plus l. Well, I think we know this by now, don't we? A is the first term, d is the common difference, d equals common difference. Oh, how do you spell common? There we go. You know all that time where I pretend to my lower 6 classes that my bad writing is because I'm writing on a whiteboard and it's really hard to write on a whiteboard. You're now seeing that actually I can't write normally anyway. So there we go. And L is the last term. N is the number of terms. L is the last term. One thing that's worth remembering, because I think we sometimes are in danger of forgetting this, A and D and L, they don't have to be whole numbers, they don't have to be any kind of particular value, but N, the number of terms, has to be a positive integer, doesn't it? Because you can't have a negative number of terms or a fractional number of terms. So while those other things don't have to be integers, that one definitely does. Right. All of those are on the formula booklet. If I had my whiteboard, I'd be putting little smiley faces next to them. They're all there for you just to remember. The next thing is a GP, a geometric progression. This time R is called the common ratio. And the bit that you get on the formula booklet is that the nth term is AR to the n minus 1. The sum of n terms is A times 1 minus R to the n over 1 minus R. And the sum to infinity you're given with this one is A over 1 minus R. And then it says that weird thing where it says the modulus of R is less than 1. Again, Core 3, alert that bit. We're going to talk about this modulus sign a lot more in Core 3. But that's basically another way of saying that R is between minus 1 and plus 1. If it's not, the sum to infinity doesn't exist and there's no point in calculating that. Okay, again, all of that stuff is on the formula booklet for you to remember. Now, notice that sometimes we talk about the sum of the first n terms. Sometimes we write that. Sometimes we write it as being the sum as r goes from 1 to n of whatever the sequence would be. I don't know, just put r in there. But of whatever the sequence is. I haven't written that terribly well, but that sigma means the sum of, and that means you start with the first value of r and you move up through all the values of r until you've added them all together. Okay, can we do the question on this one? 2 questions to look at. I think in the paper we are going to question 2. And then we're going to look at question 8 as well, I think. So, 2 says, this is an arithmetic progression question. The 10th term of an arithmetic progression is equal to twice the 4th term. And the 20th term is 44. Actually, the big thing here, the first thing to do, is that we need to start by turning this into some kind of equation stuff, because there's no math to go on there, really, is there? So the 10th term, remember that formula we just talked about? Here. Un is a plus n minus 1d. So the 10th term, u10, is a plus 9d. The 4th term is a plus 3d. And the 20th term is a plus 19d. This feels to me like we're heading towards some simultaneous equations, doesn't it? So we're going to start with the 10th term is equal to twice the 4th term. That gives me a plus 9d is 2a plus 6d. If I bump everything over to one side, I think I've got that, actually what's best? 0 is a minus 3d. Maybe that was an odd way of writing that. At the same time, we've also got this information here that says that a plus 19d equals 44. Now, you know, it's up to you. There's all sorts of ways of solving these. What do you fancy? I think I'm going to take the first equation. I'm going to write it as being a equals 3d. And then I'm going to sub that into the other one. So that means 3d plus 19d is 44. Doesn't it feel good when that happens? That's one of the great things about doing maths, isn't it? That, or especially doing maths papers, when you've set off on something and then actually you get a little pointer part way along that everything's going right. 22d is 44, so we've ended up with a really nice number as our answer for the value of d. A is 3 times that, so a must be 6. Brilliant. And then the last bit of this is just about, it said find the sum of the first 50 terms, so that's just using the formula. There it was, that's the formula we want. So the sum of the first 50 terms is n over 2, 2a plus n minus 1 times d. And you can do that in your calculator or in your head or wherever you want. I'll use my FX991 EX with the light on so that you can see what's going on. Brilliant. 750. There we go. Great. Happy with that? Just, oh yeah, sorry. Yeah. Have a look at question 8, because we're going to do question 8 now, even though we haven't done all the stuff that question 8 requires. I'm going to go slightly out of sequence with it, because I'm crazy like that. I'm wearing an orange hoodie today. That's slightly crazy. Look, it's got an X on the back for maths. There you go, so you can do maths in it. Right, question 8. There it is. And this looks awfully like trigonometry to me. And I think we can. We haven't talked about this bit of trigonometry yet, but I think we can live with that, can't we? Can we just kind of suspend our having not done that yet and cope with it? Because I think it's worth doing the sequences and series bit. So, I know it's slightly wrong, but it says you've got a sector of a circle. The angle is 1.2 radians, and the area of the sector is 60. Find the perimeter of the sector. So we need to know the radius of the sector. That's the bit that we're missing. And we need to know its arc length so that we can work this out. This is the area of a sector. Remember, the area of a sector is a half r squared theta. But theta is 1.2, so that is a half r squared times 1.2 is 60. Giving, I think, quite a convenient answer, isn't it? That we'd end up doing 60 divided by 0.6, so we get r squared is 100. R equals 10. I tend to make a big deal about when you're square rooting doing that plus or minus stuff. But why don't we need to worry about plus or minus the square root here? You can't have a negative length. We're talking about a physical length of a line here, aren't we? So it can't be negative. R must be 10. If R is 10, we need, that's those two sides, we need the arc length. The arc length is r theta. Again, that's on our poster. We've learnt that. We'll talk about that in a minute. That is 10 times 1.2. So that's 12. So I think the perimeter is 10 plus 10 plus 12. And sorry, I've squashed that in a bit, but that is 32 centimetres. And there we go, we've got a quick answer out of that. Now, what I really wanted for this question was to get on to part 2. A pattern on a t-shirt, the start of which is shown in figure 2, consists of a sequence of similar sectors. Great t-shirts with kind of maths on it. Anybody wearing a t-shirt with maths on it today? No. Right. Nobody's got. So a few people have had that. Who was wearing that Vans t-shirt the other? Are you wearing it today? No. Oh, that's a shame. Square root answer. You see, it's not really Vans. It's. There we are. Square root of the answer. Right. That should be a bit long. There we are. Okay. So the t-shirts, right, and the first sector in the pattern is the sector we've worked out about. The area of each successive one is 3/5 of the previous one. Find the area of the fifth sector in the pattern. Well, we could have just started on this point without doing part 1. It doesn't really depend on it at all. The area of the first sector was 60. That is, the first term is 60. Each sector is that the previous one multiplied by 3/5. So r equals 3/5. So we're just supposed to recognise that this is a geometric progression. And when it said find the area of the fifth sector is AR to the power of 4. That is 60 times 3/5 to the 4. And I could really do that without a calculator, but I'm going to do it. Such a nice calculator. That gives us, I think, 972/125. Are we happy with that? Yes, they accepted 7.78 as their answer. Find the total area of the first 10 sectors in the pattern. Can you see how the question here, that first one that we did, said it was an arithmetic progression and it told us what to do. This one, we had to spot it was a geometric progression. So the next bit, part B, sum of these first 10 sectors is A times 1 minus R to the n over 1 minus r. So that is, A was 60 times 1 minus 3/5 to the power of 10 over 1 minus 3/5. Again, we are going to really carefully put that into our calculator because we used to make mistakes with these things. 60 times 1 minus 3/5. Oh, I should have put a bracket around that. Hang on. All to the power of 10. Do you notice also I'm being really careful with my brackets? That gives me 149, well it's 149.1, 149 three significant figures. They allowed better, they allowed 149.1 or 0.09. Oh, I've gone again. How long ago did that disappear? Was it some time ago? Oh no, sometime around Christmas. Right, that's good, we got that. Part C. Explain why the total area will never exceed a certain limit, no matter how many sectors are used, and state the value of this limit. Okay. Well, it's a convergent series, isn't it? It's a series where the common ratio is less than 1. The common ratio is only 3/5. So as we keep on multiplying by 3/5 all the time, over and over again, the value of each subsequent sector is going to get smaller and smaller that we add on. So the common ratio is less than 1. So we've got a convergent series, convergent sequence of areas. So that means that the sum to infinity exists. And the sum to infinity, we wrote that down, it's on our poster of things, there it is. Sum to infinity is A over 1 minus R. So that is A over 1 minus R and that is, well, I think we already we knew what the answer was for that, didn't we? And if you go back and edit your previous calculation, you can probably just delete the top bit. And get 150. It kind of felt like it was always going to be 150, didn't it? Whereas that one was approaching 149. Is that all right? Great. Do you think you really can buy a T-shirt with this on it? To infinity. Oh, that would be good, wouldn't it? It kind of keeps going round. Right, there we go. Are we all right with that? How are we doing for time? So that was question 8. We've done the first 3 sections out of 6. That's good. Oh, you can't see it. There we are. Can we do binomial expansion now? And then we'll do trigonometry and integration after we've had a little break. How does that sound? Yeah. Ace. Right, okay. Do people stay ages still? No. Right, here we go. Shall we check the stream? 11 viewers! We're in double figures.
What's your record?
I don't know. I think it told me last year that at one point we had, I think they said 21 kind of concurrent viewers. So we're not quite there. Still 11. Right. Oh, it's dropped down to 10. So somebody heard me say there are 11 viewers and paused and looked at the screen and thought, that's it, I'm off. Right. Oh, we're up to 13. This is exciting. You could have a whole YouTube channel where you just do this. 14. Hang on, it doesn't count if you're here doing. Stop. Are you? Oh, 50. This is people in here, isn't it? Right. Doesn't count. Okay. Binomial theorem. Again, the formula booklet is your, I was going to say best friend, in some cases your only friend in core 2. Is that a little bit harsh? A plus B, I haven't mentioned your shirt today. Yeah. Thanks. They can't see them on the screen, so it's all right. Do you like them? I've got some really terrible shoes. Yeah.
What's up you over?
You don't. I know. Right. Mr. Robinson did say don't really? 22 it says on here. There's the shoes. Right. 24. Yeah. Okay.
Not the shoes that just really
right, this is on the formula booklet. This is what you get. A plus b to the n is a to the n plus n1. Now this is the way that they write it, but we'll talk about this in a minute. Then you get n2, a to the n minus 2b squared, plus, and then there's a little series of dots, and then you get nr, a to the n minus r, b to the r, and then it ends up with b to the n. And then underneath that, it says where nr is ncr, and that is n factorial over r factorial n minus r factorial. Now, this is the bit where John and I don't do this exactly the same way, do we? John does a kind of weird table of stuff and focuses very much on the NCR bit. It's brilliant. I mean, he's fantastic Geordie sort of chap. But I love the symmetry in this. So this is one of my favourite bits to teach of Core 2 is the binomial theorem, because I just think the patterns in here are brilliant. And I get excited about it. So if we have, if we're doing a plus b to the power of 5, then it's all about the patterns that are in there. So it starts with a to the 5, and then you get, well, you could know it was 5, but the first power is going to go down by 1. So that's a to the 4, b to the 1. So this fraction has 5 factorial over 4 factorial, 1 factorial on the bottom of it. Then the next term would have an a to the 3 b squared, because that power has gone down by 1 and that one has gone up by 1. So the fraction in front of it will go 5 factorial over 3 factorial, 2 factorial. How cool is that? It's all about the patterns. And then the next one goes a squared b cubed, because that one's gone down by 1, that one's gone up by 1. 5 factorial over 2 factorial, 3 factorial. Okay, nobody else is enjoying it quite as much as I am, but that's how the patterns all work. And that pattern means that if you wanted to do any expansion, so give me an integer between 10 and 30.
26.
26. Okay, if we did a plus b to the power of 26, now somewhere within that there would be a term where the power of the first number is 19. There'd be an a to the 19. You could write the rest of this down just straight away, because if that says 19, the power of the b term must be 7, because 19 add 7 is 26. And the fraction must be 26 factorial over 19 factorial, 7 factorial. Isn't that great? You can get any term just from the stuff that you know about the patterns and the symmetry and all that's in there. Ah, great. Good. And then all you need to do is to work out what a and b are and replace them in your expansion, and you've got every term. Why would you think of it any other way? And it's quite emotional for me, this, because you're the last people to ever do core 2. This is possibly my favourite part of core 2. You're the last people to ever do it. This is the last time I'm explaining binomial theorem in this way. We could just pause and just kind of realise, along with the 17 people who are watching on the live stream, just how exciting a moment, how emotional a moment that is. Still 17. Right. Let's do the question, shall we? It is, I don't even know where it is. Okay. It's question 4. Oh, no, actually, before we do that, sorry. Before we go straight into that, I want to remind you of something that people always get wrong. And that is, if we were doing, let's say we're doing 1 plus 2x to the 7, if we're going to find the term, what power? The term in x to the 4 that's in that. So somewhere along the line, we want to find the x to the 4 term. Okay, that could be a question. Find the x to the 4 term in the expansion of 1 plus 2x to the 7. Now, if it's going to be x to the 4, that means the 2x bit is to the power of 4. That means the 1 that's at the start of that bracket, I don't really need to write this, but the 1 would have a power of 3, because the powers add up to 7. It means the coefficient would be 7 factorial over 3 factorial, 4 factorial. That's the term that I'm looking for. And the next bit is where people get this wrong. That first bit, 7 factorial over 3 factorial and 4 factorial, if you really want to, you can do that as being 7c4 and get 35 from your calculator by doing that. Or you can think 7 factorial over 4 factorial, that's 7 times 6 times 5, because the 4's cancelled out. 3 factorial is 6, that's 7 times 5, it's 35. Times 2x to the 4. Now the bit that goes wrong here is people write 70 x to the 4 as the next line. Can you all see what's wrong with 70 x to the 4 as the answer? This 2 is also inside the bracket with the power of 4. So it's not 35 times 2, it's 35 times 16 that we should be doing. That should be 560 x to the 4 from doing that. And I just wanted to stress that point because that's such a common mistake that people do the power of the x, but forget to do it of the coefficient that's in front of it. Right, now we can do the exam question, which is question 4. Maybe only part 1. It is just part 1. Is this alright if we do this way? We're going to do part 1 now, and then we'll have a short break, and then we'll do part 2 as part of the integration. Is that too early to have a break? No. Wow, right, okay. So, part 1. Yeah, okay. X squared minus 5 all cubed. Find the binomial expansion, simplifying the terms. So this will be the first, that's a to the 3, so it's x squared cubed. The next term will be an x squared to the 2 and a minus 5 to the 1. Now, I wouldn't normally write this, but I will do just now. So that's 3 factorial, 2 factorial, 1 factorial is the coefficients. We probably know that that's 3 anyway, don't we? Our calculator will soon tell us that. The next term is x squared to the 1 minus 5 squared. And that will be a 3 factorial over 1 factorial, 2 factorial. And the last term is going to be the minus 5 cubed. It's not much of a binomial question, really. If we're careful with those terms there, that is x squared cubed. Remember, we started today with indices and with multiplying the powers and all that stuff. So x squared cubed is x to the 6. We then got 3 out of that. That gives us a minus 5. I put plus, I shouldn't have done. So that's going to be minus 15. 3 times minus 5, x to the 4. We're then going to have a minus 5 squared times 3, that's 25 times 3, so that's 75 times x squared to the 1. And we'll end up with a minus 125, because minus 5 cubed gives me minus 125. There, I think. Is my answer. And is that what they've got? Question 4 says x to the 6 minus 15x to the 4 plus 75x squared minus 125. Yes. Right. Do you want to have 15 minutes to stretch your legs and pause and go to the loo or whatever? So we're back at 25 past. Great. writing.
Eric, do you want to appear on the street?
No. Sorry. This seems tick. Tick, tick. Oh, do you not be a drink?
is there a live chat? Right, come on then. Let's sit back down and get ready to go. Okay. Shh. Shall we? We did a special Twitter photo on the Twitter thing from this morning. Can we do the same thing again? Are you all? We'll do it from a slightly different angle.
Correct.
Are we all ready? Okay, so when you get the picture, you've got to look at the back corner at what those two were doing. Right, so that I'll Twitterize that. What do I write?
Maths session, maths.
I'm writing hashtag maths in the hub. But that's what I wrote this morning. It's a bit dull to write the same thing twice. There we go. Right. I just said final sprint through the last two topics, integration and trigonometry. We're going to start with trigonometry. They're big topics though. There's a lot of stuff to do in these last two topics. So just how ready do we feel? Okay, that was about 3 in terms of. Right, Joe's ready. Excellent. Okay. Right. Trigonometry. Right. There we go. Trigonometry. Did you just see the trees?
Yeah. I was in it.
No, sorry. I was in it as well.
My hand is not in it.
Right, so given any triangle, we start with the sine rule and the cosine rule. Trigonometry is massive, isn't it, on Core 2? Look, this is the list. We're in this bit here. So we've got sine rule and cosine rule, radians, arcs and sectors, ratios and graphs, equations, and then identities. We've got loads to do as part of this trigonometry section. So we start with a reminder. If they are the angles A, B and C, and they are the length of the sides opposite them, then the sine rule says sine A over A is the same as sine B over B, is the same as sine C over C. Now, of course, when we talk about the sine rule, we could also flip that upside down, so the reciprocal of each of those is also true. That's not on the formula booklets. You have to remember that, have to learn it. This one is, though, A squared is b squared plus c squared minus 2bc cos A. That does appear on the formula booklet, so you don't have to learn that one. The bizarre thing that we get every year, a very small number of students write the cosine rule, but put sine there instead of cosine. So the clue is in the name. It's the cosine rule because it contains cosine in it. Mentioning no names. Right. So that's those two to start with. That one is on the formula booklet though, so that one you can refer to in the formula booklet. We also, the other thing that goes along with those is the area of this triangle is a half AB sine C. I'm not sure how good that formula is to remember. Really what you should be remembering is it's the two sides adjacent to the angle and the sine of the angle between them times a half. You know, that's what you should be remembering, so you can always adapt it to any triangle that you're working with. So that's the crucial thing. Okay, then so that was the first bit of trigonometry that we did. We then talked about this new way of measuring angles. We talked about radians, where when we 180 degrees is the same as pi radians, and so we should have pretty well remembered all of those conversions. You know, if we want 90 degrees, that's pi by 2. If we want 30 degrees, that's pi by 6. You can get your calculator to do it, but it's good to remember you're just looking for what fraction of 180 your angle is to do that conversion. That's the thing that you're interested in. So if you want to convert x degrees to radians, then you want to know what fraction of 180 is it, and multiply that answer by pi. And that's your method. So just kind of remember that you're doing that. If you're going to do it the other way around, of course, we need to just reverse that process. So you multiply your fraction of pi by 180 and divide by pi. So y radians, you're going to divide by pi and times by 180. Okay, we should remember those conversions. I've used C as the little thing instead of the degree of radians. You don't often see that. It's sometimes used. OCR don't tend to use that, I think. So based on the radian stuff, we had that if we have a sector of a circle of angle theta and radius r, we've used this one already today, the arc length is r theta, that's the arc length there across the top. Thanks for the warning. And r squared theta. None of this down here is on the formula booklet, so you've got to remember all of this stuff. Okay? So that's the first bit. I'm going to go on to the second slide for all of this stuff, because then, once we talked about the arc length and area of the sector stuff and area of the triangle, all of that, we get into thinking about the graphs of these things. And you should have a really good, sound knowledge of what these graphs are all about. So that's going to be the sine graph, approximately, from 1 to -1 with 0 in the middle. And these label these axes in degrees or radians. So let's say that is, I've done it in degrees for now, 360, and there's 180. So that's why. There's y equals cos x. Again from +1 to -1, and that's 90, 180, 270, 360. And tan, well, when it comes to drawing tan, I do that another way around. So instead of drawing the graphs and then marking the axes, I am going to mark my asymptotes on the axes first and use that as a guide to help me draw the rest of it. So tan from 0 and up there, and it's going like that. Now the next bit, I'm not going to get into this this argument today. I like the cast diagram. There we are, I've said it. I know that Paul and John don't like the cast diagram and prefer to use the diagrams. So it's up to you. If you want to use the cast diagram, you can. I will. I think it's a really good way of remembering how the symmetries work. But if you want to use the graphs, that's fine as well. So they're the graphs. I keep saying that transformations of graphs is the one thing that appears on all 4 of the core modules. But we don't teach it kind of separately as part of core 2. This is where it will probably appear as part of the stuff about trigonometry. So those descriptions, those of you who are here this morning, this is my big pile of paper from this morning. It's in here somewhere. Somewhere this morning we wrote, there it is, just found it. We wrote that, which was all of the descriptions of all the different transformations of graphs. And that stuff from core 1, that applies again. You know, you need to know that for core 2. And this could be the occasion. So you could be asked to sketch sine 2x or something like that. One thing to watch out for, we haven't in the past always been that clear about this, I don't think, in our teaching of this. But the words period and amplitude come into these 2 functions in particular. And so the period of a trigonometric graph, or of any graph, is how long it takes to repeat itself. So the period of these 2 graphs, period of sine x and cos x, is 360 degrees, or 2 pi radians. Notice that the period of tan x is different to that, because tan x repeats itself more often. Tan x repeats itself every 180 degrees. You're back to it doing the same thing, whereas these 2 are both 360 degrees. The amplitude, when you've got a wave, when you've got a graph that's doing that kind of pattern, the amplitude is how far it's going kind of up and down each time. So we have an amplitude of 2, the difference between its lowest and biggest values. An amplitude of 1. Did we talk about 1 or 2? 1. Yeah, an amplitude of 1. How far it's going from its middle point. Oh, I've just spelled amplitude wrong now. And that's remember.
Oh, it's gone off.
Oh, remember that when we do, you didn't warn me. When we do 2 sine x, then 2 sine x is going up to 2 and down to minus 2. 3 sine x, up to 3 and down to minus 3. So remember how that changes. This bit, about the period of the graph, we last summer's exam included something about the period of a sine graph that we hadn't maybe been as clear explaining that as we could have been in the past, because it had not really come up before as a concept that students need to know about. There's a little hint there for those who haven't done last summer's exam as a mock exam yet. Oops. Right, 2 more things to put on the bottom of here are the trigonometric identities, which would be tan x is sine x over cos x, and sine squared x plus cos squared x is always equal to 1. The bottom one, that's the normal way that you would write it, but be aware that the way that you will actually use that is you might use it to write sine squared x as being 1 minus cos squared x, or you might use it to write the cos squared x is 1 minus sine squared x. You probably won't use it in that form. You'll use it in one of those 2 forms, possibly with a stealth quadratic somewhere in there. Okay, I think we're ready to do the questions that relate to this stuff. So we're on question 1 on the paper, right to the start of the paper. Yeah. Not on now. It keeps, what keeps telling it?
She said it keeps on like freeze it and not working for
I wonder if that's when the laptop screen goes up. Oh dear.
MathsDave is working.
Great. Thank you. Okay, question 1. The lengths of the 3 sides of a triangle are, given there, 6.4 centimetres, 7 centimetres, and 11.3. Find the largest angle in the triangle. It's a slightly unusual start question of a paper, but I think quite an easy one to work with. What we'll do is I like diagrams. I think I want to draw a diagram of what's going on with this. I think that seems like a sensible way to go. So we've got a long side of 11.3, a short side of 6.4, and a slightly longer side of 7.0 centimetres. There is my triangle. If the question is going to ask me for the largest angle in the triangle, then the largest angle is always going to be opposite to the largest side, isn't it? So that must be the largest angle in the triangle. That's the one that we're after. That's theta. And it's set up as a cosine rule question. You know, you've got 3 sides and an angle. So we're going to do cosine rule, 11.3 squared, 6.4 squared plus 7.0 squared minus 2 times 6.4 times 7.0 cos theta. And I couldn't quite fit it onto the page because I misjudged. Now we need to rearrange this. Maybe we'll do some calculations first. We've got 11.3 squared (6.4 squared) plus 7 squared and then that gives us 89.6 cos theta there. So we're going to rearrange this to get cos theta on its own and then do inverse cos of that. So that's 127, these are exact values, weren't they? (37.73) is minus 89.6 cos theta. So cos theta is minus 37.73 over 89.6. I've ended up with a fraction, but I'm going to do inverse cos of that. Now, it doesn't say, does it? The lengths of the 3 sides are given there. It doesn't say whether we want our answer in degrees or radians. So it's up to us what we do with this. Inverse cos of that answer gives me 114.9 degrees. I think they're probably looking for 115. I've got it somewhere. Yep, they wanted 115 degrees or 2.01 radians or better as the answer. So there we are. Find the area of the triangle. Again, it's just a case of using that formula that we've talked about already and we've learnt. So the formula says that it's a half AB sine C, where A and B are the 2 sides adjacent to our angle. So this is just a half A, B, sine C, where the angle is our angle that we've worked out. And actually, just to be sure, there's my angle on the calculator. Just to make sure of this, I'm going to store that in a memory. We know how to do this, don't we? So that would be store, and then pick one of the pink letters. So I'll store it in memory A. So there it is. So when I now do a half times 6.4 times 7 times sine A, that should give me an exact value, 21.3 centimetres squared. There we go. I've put the wrong figure in there, haven't I? It was 6.4, not 6.7. Is that better? There we go, 20.3. Okay, it's not a bad start. That's far from essential, but I think it's a good idea to draw a diagram, isn't it? You know, I always would feel more comfortable with a diagram to help me on my way. Right, that was question 1. Question 5. There we go, we've got some more trig equations to do with question 5. I may end up with a cast diagram here, that'd be good. So solve each of the following equations for x between 0 and 180. Sine 2x equals 0.5. Okay. Thinking of common mistakes that students make, the 2x can cause people problems, and people can do a foolish thing of dividing by 2 at the start, but that's only if it's a 2x in there. You can't do anything with that until we've got rid of the sign. It's only if there's a number in front of the sign that we can start like that. Our first step here is going to be to take inverse sine of both sides. I would hope that some of you, a lot of you, will know what we get from that. Inverse sine of a half is 30 degrees. We know that we don't need to be in radians because there was no mention of radians up here. This was in degrees. We don't, or if I'm doing this, I don't, at this point, immediately divide by 2. Because if I'm going to use the cast diagram for this, and I want to know about the symmetry of the graph before I do any of that, so I'm going to think here, I know this is only applying to those who like the cast diagram. There it is, the cast diagram. Fantastic diagram. We've got sine and it was positive, so that means our angle is in those 2 quadrants, A for all and S for sine. We mark a 30-degree angle with the horizontal. And we're going, if x is between 0 and 180, 2x is between 0 and 360. So we're looking all the way around, and that gives us 30, and then the next one is 150. Because it's that angle there, it was 30 less than 180. And then we divide those 2 answers by 2. And that's our answer. And it may be that the method that you've been shown by John or Paul you feel is vastly superior to that in every possible way. I like the cast diagram. Part 2. Oh no, I can't even see where part 2 is. Was that too early with the joke? Should I have gone further? It's a stealth quadratic that we have to deal with. We've got sine squared and we've got cos. We need to get it in terms of the same thing. 2 sine squared x is 2 minus root 3 cos x. So we need to get it in terms of the same thing. We need to do something about this sine squared to get it in terms of cos, because we can't change the cos into a sine squared. So our first step, remember on that other bit of paper a little while ago, I said the way that you're going to use these things is that you're normally going to use either of those 2 down at the bottom there. And here we're going to use sine squared x is 1 minus cos squared x. Sine squared x is 1 minus cos squared x. So that tells us we've got 2 sine squared x is 2 minus root 3 cos x. Which if we simplify this, 2 minus 2 cos squared x is 2 minus root 3 cos x. Can you see that it's actually working out quite nicely? The 2 cancels out. We can get rid of the minus signs as well. We end up with cos squared x. How am I rearranging this? I'm not terribly happy with what I've just done there. I think I've done too many steps at once for you. I think it's right, but I think have I gone too far at once? Are we happy with that? 2 cos squared x, that's why it's not, yeah. Are we happy with that? If we take away the 2, move this term onto the right hand side, it becomes 2 cos squared x minus root 3 cos x. Now we want to know values of cos x from this. We're going to factorise this. Common factor of cos x, 2 cos x minus root 3. So somebody keeps pinging. So cos x is 0, or cos x is root 3 over 2, both of which are very nice values to have got. If on your calculator you do inverse cos of 0, I can't believe I'm typing it in, you get 90. You may remember the way that the cos graph works. If that's 0 at 90, then that's going to happen again at 270. But remember, x was between 0 and 180. So that's actually the only value we're interested in this case. And the other one, if cos x is root 3 over 2, inverse cos of root 3 over 2 gives you 30 degrees again. And that's your other value. And again, if we think of the cast diagram, or however you want to think about this, then there is cos at 30 degrees, and that's 30, and the next one is 330, but x is between 0 and 180. So they're the only 2 values that we are interested in. Those 2 are no other solutions. It's important that we don't put any other values in there. That's supposed to be a 30, and then I've got an extra 0 there, because I got carried along. There we are. Right. Is that the end of trigonometry as well? Wow. 5 to 3. Oh, that looks like a big question. Right, so what have we done of this this paper so far? We've done question 1. We've done question 2 in its entirety. Question 3 we've done. Question 4 we've done part 1 but not part 2. Question 5 we've done. Question 6 is still to do. Question 7 we've done. 8 we've done. 9 is still to do. So we've got question 9, 4 part 2, and whatever the other one was. 6. Right. Integration. Is the stream working now? Have you had a reply? I wonder if it was here. I'll try and keep that only when the screen goes off in the laptop. I'll try and keep doing. Okay, integration, final topic. Again, we start just by thinking about our basic rules of integration, and some of what I said this morning is going to apply all over again. Because this morning, if you remember, we made the point that sometimes with these things, it's the power stuff that loses us. It's the how we deal with indices that we go wrong with. So, our basic rule, it's on our poster, says that if integrate x to the n, you add 1 to the power and divide by the new power. You then must always remember to write plus c if you're doing an indefinite integral. And, although it doesn't really matter at this stage, this rule is only true if n isn't equal to minus 1. If n is equal to minus 1, then we'll do about that in core 3. That's coming up next year. It's good, isn't it? Good. Right. Again, just kind of a quick thing. Where might we go wrong? What kind of questions might they be asking that they know students are going to make mistakes on? And one of the key areas that we know students will make mistakes on this is if we do the integral of what can we have? 1 over 3x squared dx. If we try and do that integral, And the reason that we'll get that wrong is not because we can't integrate well enough. The reason we'll get that wrong is we won't do the first step right. 1 over 3x squared is not 3x to the minus 2. We talked about that this morning as well, didn't we? 1 over 3x squared is 1/3 x to the minus 2. So it's really important that we remember how to separate it, how to turn it into an index form calculation for us to do something with. Now we can add 1 to the power and divide by the new power and put plus c in there. Okay, but before, that's the step, I think, where we're most likely to lose marks on this stuff. So be really careful about some of that. Again, the other thing that links in with that is being really careful about fractions and dividing by fractions and how you deal with that. So if we had to do the integral of x to the quarter dx, yeah, I was kind of just made it up, so I wasn't making a big deal of it. But that's the Jacob just pointed out that the issue with this 1 over minus 3. It's the minus sign. Is that what you're saying?
No, the third x is part of both, isn't it?
The third x. Hang
Is
on.
it not the third x all over times?
No, because it's this is just a constant multiplying. It's a third times x to the minus 2. When you integrate 2x squared, you add 1 to the power and you divide by that, so it's 2/3 of that. Here we've done a third divided by minus 1. Yeah, are you okay?
I take on.
Yeah. But actually, there is a point in this. Again, it's quite a rare thing, and it's a really picky thing, but the idea of having a fraction with a negative sign on the bottom of the fraction, that actually we don't really like that. It's not very nice. Not a nice way of expressing yourself mathematically. So this answer here is better. It feels like there's nothing happened there. But if you've got 1 over minus 3, it's much better to write it as being minus a third. And I think, it can't remember if it's core 1 or core 2, but I think there has been one occasion where a mark has been denied for writing it like that rather than like that. So just be a little bit careful about how you write your minus sign at the end of it. You could also write that as being minus 1 over 3x plus c, because it's the same as that. X to the minus 1 is 1 over x. Right, this example I was going to give, if we add 1 to the power, what's a quarter plus 1? 5 quarters, yeah, 5 over 4. Right. So we've got x to the 5 over 4. The next bit is what catches people out as well. We're dividing now by 5 over 4. Now if you want to, you can write that. That can't be how you leave your answer, but you could write that. Then remember, this is going way back to what, year 6, year 7? When you started dividing by fractions for the first time, and you were taught that if you divide by a fraction, you multiply by its reciprocal. You maybe didn't use the word reciprocal, but that's what you were told to do. So dividing by 5 over 4 is like multiplying by, thank you, 4 over 5. There it is. So that would be our answer to that one. It is, of course, fine to go straight from that line to that line. You don't have to have gone through the 1 over 5 over 4 bit. Okay. What we talked when we did differentiation this morning. We talked a bit about how we might use differentiation, how we spot we're going to use it. Integration, really, we're only going to use it on 2 occasions in core 2. We're going to use it to undo differentiation. So our question is going to start by saying dy by dx equals, and we have to undo that and go backwards to get what y equals. Or we're going to do finding areas. And if we're finding areas, then what we're saying is we have some curve and we're finding the area bounded by the curve and the x-axis. So if these are the points A and B, and this is our equation of our curve, then where y equals some function of x. Actually, I'm going to write this as, it's a slightly odd thing to do, but I'm going to write that as y equals f dashed x. Then the area is the integral from a to b, from the bottom limit to the top limit, of y dx. If you're asked to find the area bounded by the curve and the y-axis, you do it as x dy. If we integrate that, that will give us some answer when we integrate, and we evaluate it by subbing them in, and you sub in the upper number, take away the lower number. And that gives us our value. Okay? So when some people sometimes get confused about the order that we put our limits on. So when you're putting the limits on, you're going from the bottom of the integral to the top, from the lower value to the top value. But then when you do your subtraction, it's a bit like being back in school again, kind of pre-calculated days. If somebody asked you to do 17 take away 5, then you would have written it like that, wouldn't you? You'd do 17 take away 5. Can you see the link with this? So you're going, if you're doing from the integral from a to b, then we're doing b take away a. We're doing 17 take away 5. From 5 to 17, difference from 5 to 17 to 17 take 5. Did that help? I'm not sure that it did. Anyway. So that's that. Then the last bit of integration is the trapezium rule. And if we think of how our year has gone on this year, then the trapezium rule was what you did in the first week of February, first and second weeks of February, just before half term, to mark the end of core 2. And it's in the formula booklet. It says the integral of y dx is approximately equal to 1/2 times h times y0 plus yn plus twice y1 plus y2 plus yn minus 1, and then the bracket closes. And that's what you're given. Don't worry too much about h. H is just the difference between the steps, the difference between the x values that you're using. So it's not a big deal to calculate h. There's a little formula that goes next to this in the formula booklet. But you're better just writing down your x values and finding the difference between any pair of them and doing it that way. That's the easiest way to come up with h. And this will give you a numerical value that represents the area. One final thing about this, you know, you've seen the question, is your area, is your value an underestimate or an overestimate of the area? And I think the best way of answering that question is clearly to state whether it is, but then to draw a little graph, draw a little diagram. So if your curve is going like that, then the tops of the trapeziums would be underneath the curve. Can you see how they were going underneath the curve? If the tops of the trapeziums are under the curve, that's giving you an underestimate. If the curve is going that way, then the tops of your trapeziums are going to go slightly over the top of the curve. I've exaggerated it a little bit, but there you go. And so your estimate is an overestimate, because your trapeziums are above the top of the curve. Does that make sense? And there we go. Are we ready for the last questions? Well, I've had 6 interactions about that tweet. Wow. Exciting. Which ones did I say? Question 4, part 2. Should we start with that one, and then we go back questions on? So this is back. We did 4, part 1 earlier. Do you remember? happening. Four likes for saying why is... Right, are we ready? This question said find, it said hence find the integral of x squared minus 5 cubed dx. So remember, it feels like a long time ago now, we expanded the brackets of that, we did the binomial expansion, and we got that as being the integral of x to the 6 minus 15x to the 4 plus 75x squared minus 125 dx. And it's not a particularly difficult integration question. They're giving 4 marks for this. That's 4 marks for not much at all, isn't it? We're just going to add 1 to the power, divide by the mu power, add 1 to the power and divide by the mu power all the way along. And of course 125 goes to 125x, and we must remember to write plus c at the end of it. We ought to simplify our coefficients. So the last thing to do is to say this is x to the 7 over 7 minus 3x to the 5 plus 25x cubed minus 125x plus c. There we go. That's quite a nice start, isn't it? And they load it up with marks, you know. You had to have plus c, but I think that's a really easy 4 marks. Great. Are we happy with that? Did my register go all the way around, by the way? Has everybody signed the register? It's there. Good. Did anybody not get the register? You two didn't get the register. Tom, it's over there on the very back corner. Do you want to go and get it? Good work. Right. That was 4 sorted. Question 6. $12 viewers at the moment. Okay, the gradient. Now, do you remember I said a few minutes ago, it's on video, I said that what might we be asked to do with integration? One thing is we may be given dy by dx equals and asked to undo that. The other thing is to find an area. So here we go, this is the dy by dx equals. Notice again, it was kind of a little bit of a point this morning. Quite often questions don't explicitly tell you what to do. So this morning we did a differentiation question that didn't mention differentiation or gradient or stationary point or any of those things. And we had to work out how we were supposed to start it. So this one, we've got an integration question that doesn't mention integration. It starts with dy by dx is 3x squared plus a. And we need to proceed from there. It's this lack of scaffolding. 8 marks. Just kind of, here's the problem, go and deal with it. So we recognise that to undo dy by dx, we have to integrate. We are going to get a couple of marks just for integrating correctly. And I think, right, so just integrate this yourself, because I think now there's going to be a really common mistake. So what do we get when we integrate this? First bit's easy. And if you've been brave enough to write something down, I reckon that probably the majority of people have now got ax written, but a small number of people have got a squared over 2 written. Anybody got a squared over 2? Nobody's going to admit to it because I've given the impression it's wrong. But Tom got a squared over 2, did he? That would be a really common mistake with it. A is a constant. A is just a number. Okay, it's not a variable, it's not an x thing. So when we integrate it, if that had been 3x squared plus 3, you would have been quite happy to put 3x there. It's just a number like 3. So that is ax plus c. And that would have been a really common mistake in the exam on this question. It's something to really look out for. Right, we've got an equation of the curve, but it's got 2 things that we don't know in it. Fortunately, we've got 2 bits of information to help us. So if x equals minus 1, y equals 2, that tells us that 2 is minus 1 minus a plus c. How do I want to deal with this? I think I'm going to say that 3 equals minus a plus c, and leave it like that for now. And if x equals 2, y is 17. So 17 is 8 plus 2a plus c. Is that right? Subbing that in. So 17 take 8 gives us 9. Equals 2a plus c. What should we do? Let's call these equations 1 and 2. Oh, did you know this? Yeah. Just a quick kind of calculator advert. Oh, the lamp's still on. There we are. I don't know if you've seen this before, but this is quite a neat little thing. If you go back into that equation thing, and we go to simultaneous equations, which is option 1, we've got 2 equations and 2 unknowns, so I'm going to press 2 for the number of unknowns, and it's in terms of x and y, so that's a, b, our x bit, so that's minus 1a and 1y, and that's equal to 3, and the other equation says 2a, 1y, and it's equal to 9. Oh, it's gone again. Oh. So is this.
Yeah.
There, did you see how I typed all of that in? Equals 9. And now if I press equals, it says x equals 2, y equals 5. It's the solution of my simultaneous equations. How cool is that? It's quite cool. Right. We're going to solve these. I'm going to solve these by doing equation 2, take away equation 1. It gives me 6. It's 3a, so a is 2. If I sub that back in, therefore 3 is minus 2 plus c, so c equals 5. And that just confirms what the calculator told us. But that's quite a neat thing to be able to do on the calculator, isn't it? Just to check your simultaneous equations. So, have I done it? How many marks have I got now? I think 7. Because the question didn't say find a and c, the question said find the equation of the curve. So I have to actually go back and write y equals x cubed plus 2x plus 5, and there it is. All right, any questions? Does this, I'm hoping this all feels kind of doable, these questions. You know, that's 8 marks there, and if you just take it steady, clearly write things out, it's definitely 8 marks that we could get, isn't it? Right, that was question 6. Question 9, right at the very end of the paper. And I did say that you're supposed to have expanded your list of graphs that you know. We wrote it down as one of the core 1 graphs, but the graph of a to the x is one we should be able to do. It should be on our poster. We talk about an exponential graph. Not a good set of axes, but there we go. And so it's a graph that goes something like that. Now this graph, if that's the graph of y equals a to the x, that would normally cross. Let's think about what happens if x equals 0. So here on the y-axis, if x equals 0, we've just drawn 4k to the x. If x equals 0, that's 4 times k to the 0. Anything to the 0 is 1, so that's 4 times 1. That's the point 0, 4. And there's our graph draw. Now, one thing to point out here. This, I can't remember what this was. I think this is in one of the ones we used as a retest for either core 1 or core 2. But there was a point where you had to sketch a graph, and you had to mark the coordinates of the point where it crossed the coordinate axes. And I had a student who marked it, like in this question, marked the number 4 at that point and didn't get the mark. Because the question didn't say mark the y coordinate, the question said state the coordinates of any points of intersection with the axes. And the coordinates is not just y equals 4, that's x equals 0, y equals 4. You have to give the full pair of coordinates. It's really harsh, but you have to do it. The mark scheme here only said state or imply 0, 4. I think you may have got away with just writing 4 for this one, but maybe don't take the risk in future. Just a little thing while we're talking about that. If that's the graph of k being greater than 1, so that's the y equals a to the x if a is greater than 1. What would it look like if a was between 0 and 1? Have a think for a moment. No, you know, Jacob. What would it look like? Yeah, if a was between 0 and 1, you would end up with a graph. I'm not drawn that very well. But you'd end up with a graph. There was a reflection in the y-axis of that. So that is y equals a to the x for a between 0 and 1. Okay, it's just a reflection of that one in the y-axis. Right. For a number of really good reasons, one way you can think about that is if a is between 0 and 1, then you could always write it as its reciprocal, and its reciprocal would be bigger than 1, but that would now have a minus power, so it's a to the minus x. So that's another way of thinking about it. Right, part 2. The point P on the curve, y equals 4k to the x, has y coordinate equal to 20k squared. So that the x coordinate of P may be written as 2 plus log k 5. This is our logs question. Remember we skipped logs earlier on. We didn't do this question. We said it was logs, but we missed it. Right. This is quite a hard question. I think maybe this part is one of the hardest bits on the paper, if I remember this paper right. So y equals 4k to the x. If y equals 20k squared, we need to find the x coordinate. That means 4k to the x is 20k squared. We need to find x. The tough bit here is that we've also got k hanging around and we don't know much about k. Our answer needs to include k. To start with, I think we need to get rid of this 4 and this 20 at the start. So let's divide both sides by 4. It's always good just to get rid of any constant that's hanging around. Now, the question would like us to write our answer in terms of log base k. You see we've got log base k there. Now I know earlier on I said take log base 10 of both sides because that's the easiest way to do these things. Are we alright? But for this one we're going to go with log base k because log base k appears in our final answer. So let's put log base k in front of both sides. Now there is loads of room for us to do some quite tricky things with this. There's loads of places where this could now go wrong. So we're going to have to be really, really careful. Log base k of k to the x, we can bring down the x to the front. That's okay. Log base k of 5k squared, can we bring the 2 down to the front? It was great how there was the answer of both yes and no coming out then. From the same person. We can't bring the 2 down to the front yet because it's that whole thing of it being a whole power. If it was 5k all to the power of 2, we could bring the 2 down to the front, but it's not. We need to split it up first. It's log base k of 5 plus log base k of k squared. Can you see how that matters, how that was important to start with? Because the 2 only applied to the k. It was only a power of the k, not a power of the 5. Right, we're getting there. What's log base k of k? 1. That's log base k of 5. That is 2 log base k of k. And log base k of k is 1, so that gives us that, which is what we're supposed to get up at the top of the page. That was a tough bit of a question, and it was tough because they gave you the answer and they're really strict with this. You know, I remember marking this when we used this as a mock exam, and getting, you know, maybe 3/4 of the students who attempted this part of the question got to that answer, but maybe only 1/4 of those answers were actually correct working along the way, because the rest of them had made a mistake in the manipulating logs and had lost the marks. So as soon as you do that thing that we just talked about, as soon as you do that thing of saying log base k of 5k squared and then bring the 2 down there, now even if you then go from there and end up with the right answer, you're going to score 0, because you're not allowed to get the answer with wrong working. It will say it in the mark scheme, probably. Well, it doesn't particularly mention it at this point, but quite often they include, have you seen the WWW abbreviation appearing on mark schemes without wrong working? And so you're not allowed to arrive at a correct answer with wrong working. You're not going to get away with that. You're not going to fluke it. Right, there we are. So that was that bit. Part 3. It says, use the trapezium rule with 2 strips, each of width a half, to find an expression for the approximate value of the integral from 0 to 1 of 4k to the x dx. Can I go on the back? Yes. Right. So, it doesn't rely, fortunately, on what we've just done. 4k to the x, the integral from 0 to 1. This is just trapezium rule now. It's ridiculous doing trapezium rule with 2 strips because it's kind of almost not worth doing the trapezium rule. But anyway, it's maybe over the top with this one. I like doing a little table of my values just to remind me about where I'm putting them. So if it's 2 strips and it's from 0 to 1, it must be 0, a half and 1 as my values, because 2 strips needs to have 3 values, because we need to be able to separate each strip with a value at the start and end of it. Y is 4k to the x. So if we put 0 into that, 4k to the 0 is 4. If we put a half into that, we get 4k to the half. And if we put 1 into it, we get 4 times k. Notice it's fine with using k in this value. Now we do the trapezium rule. So the area is approximately equal to a half times h, which is also a half in this case. And this is why I like the table for this, because it reminds me that the first two values I'm going to write separately. So 4 plus 4k are the first and last values I'm going to write separately. And then it's twice all the values in this column, which is only one value, but anyway. And that's my trapezium rule expression. I now need to simplify this. So this is a quarter times 4 plus 4k plus 8k to the half. And if I get rid of that bracket, I've got 1 plus k plus 2k to the half as my answer. That's fine. It may be nicer to write it in ascending powers of k, but anyway, that'll do as an answer. Right, are we ready for the very final bit? Given that this approximate value is equal to 16, find the value of k. Alright, so that's just saying that whatever we've just found is equal to 16. Whatever we've just found is equal to 16. Find k. And at the end of core 2, having done all of that, this is the last part of the last question, we end up with another stealth quadratic. This is a quadratic equation in terms of k to the half, isn't it? If we rearrange it, it says that we've got k plus 2k to the half minus 15 is 0. What do we want to do? Do we want to use another letter? Shall we use t? I used t earlier, I think, that t equal k to the half. That means that t squared equals k. And so if we sub that in, we've got t squared plus 2t minus 15 is 0, and we're factorising all over again. It's an easy one to factorise. 5 and minus 3. I think this is that. So t equals minus 5 and t equals 3 are our solutions. Now we need to be really careful about how sensible these answers are at the end of this. So this is t. K is equal to t squared. So k is equal to the square of each of these. Which is going to give us 25 and 9. But actually, let's kind of think through where we've gone with this. So k is t squared, but we're also saying that the square root of k, t is the square root of k. There we go. Now that's fine there. The square root of 9 is 3. But the square root of 25, we're not going to get minus 5 out of that. We need to be a little bit careful about the values that we're dealing with here. And I think this value of minus 5, k to the half is minus 5. Yeah, look. K had to be a number that was greater than 1, its square root can't therefore be minus 5. I think we need to dismiss this value. This value isn't a valid solution to our expression at the end of all of this. That is the only answer that's acceptable. Does that make sense? We're saying here that t is equal to the square root of k. Okay, but k was bigger than 1 from over here, and if k is bigger than 1, its square root can't be minus 5. But it can't be both at once. That wouldn't have given us that graph. It can't be the negative square root of that number. Yeah. But only if plus and minus is the valid solution. Everybody's going. Well, hang on, just before we go. The register, did the register come back to the front? It's there. I hope that's been a useful thing. Of course, now you've got, what is it? It's the 10th of April. You've got a month and a half until it's the 11th of April. You've got a month and a half until the exam for Core 2. There needs to be this isn't the end of your maths for this holiday. So the next bit of holiday time, you've got to follow this up. You can't just think that you've spent, for some people, nearly 6 hours doing maths today, and that's it. You know, that's kind of built up your quota of maths for the holiday. You've now got to go away and put this into practice and apply some of these things to some past papers and put the practice in. I spoke to my groups at the end of the term about setting a revision timetable and sticking to it and doing, some hours of maths each day, regular times during the week, and stick to that timetable. It's really important that you don't just think you've put a lot of time into maths now so you can ease off it. Actually, this is just the start. This is the kickstart to the rest of the run up to the exams. And it's not that long. 6 weeks time, we'll be just about done. You'll still have S1 to do in 6 weeks time, but we'll be close. 8 weeks time, we'll be pretty much all done. Your maths exams. That's not long to really commit to it. So put that time in now. I hope it's been useful today. Have a good holiday. Thanks everyone. I think part of it, how do I end the stream? Oh, this is still live.